Hello everyone, welcome to lecture number 7. So we have been developing the language of thermodynamics as it is required for our material synthesis, just to give you an overview of what has happened so far. And so we said we started developing laws of thermodynamics, the first law, the second law for the entire universe, for the entire isolated systems, as ds is always greater than or equal to 0, and systems go towards a state where ds equal to 0, that is the equilibrium state, right. So that is what we defined the second law as. It tells me the direction of the systems, right, the direction of in this case an isolated system or the universe always goes towards that state where I maximize my entropy. Okay. Then we said, look, okay, so one thing is to talk about universe if we are astrophysicists or some kind of high energy theoretical physicists, we speak about ds of universe, but in real material synthesis and material thermodynamics, we have systems, we have surroundings, and what we really care about are systems, right. So in this process we said, all right, so let us consider first closed systems. I mean, open systems also the same thing is valid. We will start open systems very soon in the next couple of lectures. And we said, look, instead of defining the second law of thermodynamics as delta S is greater than or equal to 0, which is delta S of both the system plus surrounding, I would like to define newer potentials, right. So new thermodynamic potentials, or the so called free energies, that just depend on the system, right. And so whatever the surroundings has to offer, surrounding is a reservoir that has a constant temperature, surrounding is always under equilibrium, surrounding has a constant pressure or constant so whatever it is, so that constraint gets imposed on the system, right. So the surrounding temperature just goes into my equation, the surrounding pressure just goes into my equation, right. In that sense, we have defined a couple of new potentials, right. So one of them called the Helmholtz free energy, and we said Helmholtz free energy dF, just to recap, right, Helmholtz free energy dF is dependent upon volume, right, as well as it is dependent upon temperature. So it will be P dV minus P dV plus S dt, right, whenever minus S dt. Okay. So the way I go from one equilibrium, this is by changing the external constraints, right. So Helmholtz free energy, typically in a system with a constant volume and constant temperature, this system goes towards a state where Helmholtz free energy is minimum, right. Helmholtz free energy doesn't change anymore, but Helmholtz free energy is as minimized as possible. That is the equilibrium state of the system, right. As a function of time, the equilibrium is defined. The system is initially at a non-equilibrium state. I am doing some sort of a chemical explosion reaction, right. So explosion happens, everything is equilibrating, and the equilibration takes it to such an extent that Helmholtz free energy is minimized. Okay. That is, I am not changing the external temperature, I am not changing the volume of in which the system is there. Okay. However, if I were to change the external temperature and volume to another to define another equilibrium, right. So that is where this equation is valid. So this tells me how I can change, so how the Helmholtz free energy, the new Helmholtz free energy, right, to which the system should be minimized to, depends on the volume and temperature. So this defines new equilibrium conditions. Okay. Now under those equilibrium conditions, right, so at a different temperature, different volume, maybe my explosion reaction is no longer spontaneous. Maybe my molecules are not going to react spontaneously, because the Helmholtz free energy that I am at is already lower than the equilibrium Helmholtz, or is already the lowest that I can achieve, or something like that, right. So I can change the goalposts of equilibrium, and this is what tells me how I can change the goalposts of equilibrium. Okay. Similarly, we have said then that we have moved to Gibbs free energy, and we said Gibbs free energy, by changing the external constraints, Gibbs free energy G is then dependent on T and P, the pressure, right. By changing the external conditions, Gibbs free energy can be defined as minus S dt plus V dP, right. The way to change Gibbs free energy, the way to go to new equilibrium defined by Gibbs free energy, is by changing temperature and by changing pressure, but then how you know, so how does Gibbs free energy change with temperature? Dou G by dou T at a constant dou G by dou T at a constant pressure goes as minus S. That depends on the entropy of the system. Okay. Similarly, dou G by dou P at a constant temperature, that goes as V. That is the volume of the system or inverse of density of the system. Okay. So, so you know, by changing the pressure, the volume automatically you know, so volume of the system times the change in the pressure, right. So, that is what tells me how little have I changed, how differentially have I changed the Gibbs free energy. Okay. So, this is to go towards a new equilibrium, right. So, this defines equilibrium to equilibrium hopping is what this reaction defines, or this equation defines, right, and this is gotten by changing the external constraints. So, I change the temperature, I change the pressure. Okay. But at a constant temperature and pressure, right. So, which is what happens in my you know, growth chambers typically. I can control the temperature, I can control the pressure. At a constant temperature and a pressure, the system or the chemical reactions or the phase transitions will move to an equilibrium condition, and that equilibrium condition is defined by dG equal to 0. So, G keeps reducing, right, and you know, G keeps reducing as a function of time, and at some point, just like entropy keeps increasing as a function of time, but G is just for the system, right, keeps reducing, and at some point of time you know, the delta G goes to 0, and that is what defines your equilibrium. Okay. So, my system gets stuck at the equilibrium, or whatever is the equilibrium point, my system gets stuck there. Okay. Then to change it to some other equilibrium, I have to change the temperature and pressure, right. So, then to, you know, I have to redefine my my reference equilibrium points. Okay. So, this is where we left in the last class, and you know, we said any growth, you know, any physical vapor deposition, or you know, so standard growth processes or chemical vapor deposition growth processes happen with a total control on temperature and pressure. And temperature, you know, so I can change the, you know, so I can do growth processes. That is why I do growth processes in furnaces. All these furnaces are equipped with what are called thermocouples, and this thermocouple can give me temperature of the furnace, right. So, let us say this is a resistively heating furnace, right. So, this is some kind of a tube furnace, right. So, there is a tube here, there is some kind of a heater element here that is heating this tube, right. And you know, so how much, and then this is all boxed, right. So, this is all in a box, right. This is a tube furnace. I can connect it to some kind of a vacuum system. There is a pump here, and you know, so I can also connect it to some kind of a flow line. I can flow some carrier gas such as argon or nitrogen or oxygen or something like that, right. So, I have a carrier gas, I put my precursors here, right, and you know, so I create a vapor out of these precursors by heating it, let us say, and you know, so I put my substrate here. This vapor gets transported and gets deposited on my substrate, right. So, this is the standard, you know, vapor transport processes. Right. In this entire system, what can I control? I can control the temperature. How can I control temperature? I have a coil, right, that can heat the furnace. The coil will, or the resistive heater, I supply some current to this, right. So, I supply some current to this, and this current is going to heat the coil, and this coil is going to heat the furnace, but I want to heat it to a certain temperature, right. So, there is what measure, so I need to measure the temperature. A thermocouple measures the temperature. And all this is fixed to what is called a control system. I told you about the PID controls, sort of, right. So, you know, and these PID controls, you know, so it is a proportional integral differential controller. So, whenever the temperature, so I set a temperature set point, and whenever the temperature overshoots, this will, the control system will kick in and try to, bring the temperature down. Whenever the temperature undershoots, the temperature control will kick in and try to get the temperature up. So it will, so here the heat source is switched off, here again the heat source off, or current is reduced, current through the coil is reduced. Here the current through the coil is increased, right. So as a result I square R increases, right, and so on and so forth, so that I eventually get some kind of an equilibrium temperature distribution, equilibrium temperature, right. So this is how I can control the temperature using a control system, using a measurement. So I need a measuring system, I need something to heat, something that can change the temperature, but I need to know how much temperature am I changing. For that I need a measurement system, right. So first is a source of heat, second is a measurement of temperature, and third is a control system, and with these three together I can exactly set the temperature that I want in my system, right. So in my vacuum system, or in this case in this furnace, right. So temperature is hence experimentally under my control. Okay. Similarly, what else can I control? I can control, I cannot really control the volume of a material that is being deposited on my substrate, right. So the substrate is here, the material is coming and depositing from a gas phase, let us say, right. So one layer is deposited, second layer is deposited, let us say it is a layer by layer deposition, third layer is deposited, and so on. So the volume of the material of the system keeps increasing, right. I do not have control over volume. Of the system. The system of interest here is for me this thin film, right. This thin film that I am trying to deposit is the system of interest. Okay. So I do not have control over the volume. So as a result, so Helmholtz free energy, so if I am doing this reaction in a computer, I exactly know how many atoms I am going to put, how, so I can exactly constrain the volume of the system where, this growth should happen or reaction should take place, right. But inside a growth chamber in experimental conditions, I do not have control over the volume of the system. Rather, what I can control, however, the other parameter I can control is pressure is a controllable parameter, it is under my control, right. So how can you control pressure? So first of all I have some sort of vacuum chamber earlier, right. So this whole quartz tube, right. So I said I am going to connect it to a vacuum pump, right. So that is also a vacuum chamber in some sense, right. So vacuum chamber can come in different shapes, right. So it can be spherical, it can be cylindrical, it can be this tube, whatever it is, wherever, I mean I should be able to remove off air from this vacuum chamber, right. Now so let us do this simple calculations. Under STP, standard temperature and pressure, right. So if I have, that is so 1 liter of my chamber, right. So 1 liter of my chamber would consist how many air molecules, right. So this will be Avogadro number of air molecules, right. That is about 6 times 10 power 23, I am just going to write it as 10 power 23 molecules. Okay. So this is 1 atmosphere. Now what do these vacuum pumps do? Vacuum pumps are going to pump out the air molecules, and that includes nitrogen, oxygen, it is hard to pump out water vapor, but that also exists, right. So, I want to keep my chambers as dry as possible. If there is water vapor, it gets absorbed onto the chamber walls, and that is hard to pump, but still I need to. If I have to do it, I have to do it, right. Then so other trace gases, all these are the ones that I want to pump out, right. So, I want to actually pump out using a vacuum pump. Now, what are the various types of vacuum pumps we said? Sorry. We said there is something called a roughing pump, right. These can be oil pumps or scroll pumps. The simplest of vacuum pumps that is going to take my pressure from the atmospheric pressure to about 3 orders of magnitude lower, right. So, I am going to get about 10 power minus 2 to 10 power minus 3 millibar of pressure or torr of pressure, right. Now, let me just write it as torr. Now, which means so how many molecules are still there, right. So, I started with 10 power 23 air molecules, or 1 atmosphere is about 760 torr, and so let us also get 2 millibars, and 1 atmosphere is about 1000 millibar, right. To be precise, it is 1013.25 millibar, okay. Or 1 bar, essentially 1 bar is 1 atmosphere, okay. So, now I am going to get to 10 power minus 2, okay. So, let us stick to 1 unit, torr or millibar, right. So, they are similar, it is either 760 torr or 1000 millibar. So, I can sort of interchange between the units, the order of magnitude is going to remain the same, okay. So, let us say I am going to go to 10 power minus 2 to 10 power minus 3 torr, and that means I am going from 760 torr to about 10 power minus 2 torr, right. So, this is about 10 power 3 torr roughly, right. So, in terms of order of magnitude. So, I am going to so just by using a roughing pump, I am going to reduce the pressure, the number of air molecules from in 1 liter 10 power 23, right, number of air molecules. Now, it is a large number, right. So, I want you to get a sense of what 10 power 23 is. 10 power 23 is huge, right. If I have 10 power 23 rupees with me, I will not be teaching, I will not be doing anything, right. So, I will rather sit at home and enjoy my life, right. So, 10 power 23 is a huge thing. I mean 10 power 9 is a billion, 10 power 12 is a trillion, and trillion dollars is like the GDP of a country, right. And 10 power 23 is 10 orders of magnitude larger than a trillion, or 11 orders of magnitude larger than a trillion, and I am talking about so many number of air molecules, right. If air molecules were my currency, I would have hell a lot of currency to sell and make profits, okay. But everyone has it, right. So, then that's a level playing ground. Okay. So, I have 10 power 23 air molecules, and from 10 power 23 just by using a roughing pump I am coming down to 10 power let us do this exercise 18 to 10 power 17 air molecules, right. Again not nothing, 10 power 17 to 10 power 18 air molecules is what I use a roughing pump and I can just get to it, okay. Now, then the second stage of pumping, once I pump out these first 10 power 6 molecules, right. So, at a stage where I have about 10 power 17 to 10 power 18 air molecules, which is equivalent to a pressure of 10 power minus 3, 10 power minus 2 to 10 power minus 3 torr, right. So, I use what is called a turbomolecular pump or a cryo pump, right, to further pump it down to 10 power minus 6 to 10 power minus 7 torr, or here also about 10 power minus 7 to 10 power minus 8 torr, right. Now, how do each of these pumps operate is something that you can just go check out Wikipedia or check out ChatGPT and try to learn by yourself, right. So, it is not so everything has a nice inbuilt mechanical principle by which it can flush out the air, right, or either I am just absorbing air molecules onto the walls, like it happens in a cryo pump. I'm cold on the walls, so once I'm cold on the walls, the air molecules just come and there is more absorption onto the walls, right. As a result, inside my vacuum chamber I don't have air molecules, they're all adsorbed to the wall, lot of them, right. Or I am just rotating fast enough such that I am just flushing out the air, right. So there are various different mechanical mechanisms by which all these pumps work, and everything is interesting in its own accord. Okay. So I am not going into details, but so I want you to go read up yourself, right. So just do a self study of how each of these pumps work. Okay. Let me put it in some other color so that you understand that this is what you should do. All right. Okay. But do it. I mean, it's not that so everything that you do doesn't need to be graded. Some of them are just for curiosity, right. So understand it, and next time you see a vacuum pump, you anyway you're going to ask the correct questions. You're like, oh, is this a scroll pump? Is it a roughing pump? Is it so how does it work, right. So I actually know how it works, right. So you'll be so your curiosity is sort of quenched. Okay. Now what is 10 power minus 6 to 10 power minus 7 torr in terms of the number of air molecules? So that will be so 3 orders of magnitude less than 10 power minus 3. So that will be about 10 power 14 to 10 power or 10 power 13 to 10 power 14 molecules of air, right. And this is typically the base pressure. So for lot of synthesis processes, first you pump down the chamber to base pressure, right. So first you remove off all the junk, right. So first gets pumped to what is called the base pressure, right. Now this base pressure, let us say I am growing a material like like I said, right. So one of my favorite materials is BaTiO3, right. So for BaTiO3 the base pressure of 10 power minus 7 torr is good, because anyway I am going to put in oxygen into the chamber, I am going to put in titanium or I am going to put in titanium oxide or whatever titanium, and I am also going to put sources of barium source, titanium source, right. Anyway I am going to put oxygen, so it does not make sense to keep on removing a lot of this oxygen and nitrogen from the chamber, right. So about 10 power minus 7 is reasonably good enough. Then I am going to put my own oxygen, my own pure oxygen, right. So I have removed all the water vapor. By 10 power minus 7 I can be sure that I have removed lot of water vapor and all these other things that can interact with my material and cause unnecessary doping, right. So for growing an oxide like barium titanate, a base pressure of 10 power minus 7 is good enough, let us say, okay. But for growing something like so one of my colleagues, she grows what are called topological insulators. Okay. You can check out the name Dhavala Suri, right. She is a colleague of mine. She does what is called molecular beam epitaxy. To grow very layer by layer thin films of bismuth selenide. Okay. Now to grow layer by layer thin films of bismuth selenide, so the way molecular epitaxy works, molecular beam epitaxy works is you need atomic or molecular sources of bismuth, right. You need molecular source of selenium, right, and then you react both of them on your substrate, right. So then so for every, then I have to set my pressure such that for every 2 atoms of bismuth 3 atoms of selenium go, and so that is the proportion I maintain, such that on my substrate I have 2 bismuth and 3 selenium reacting to form bismuth selenide, right. I say it in such an easy way, but so to optimize these conditions where for every 2 bismuth atoms 3 selenium comes, and through these what are called diffusion cells, and so these molecular beams that come out, so this is a hard process to optimize, right. So but so there are experts and they do this quite well, right. Okay. Now the question to you is, all right, so I want for every 2 atoms of bismuth I want 3 atoms of selenium, but it turns out that if I have oxygen in the chamber, right, the other competing compound is something like Bi2O3, right. This is the competing compound which I do not want to grow, right, especially when my pressure is 10 power minus 7 torr, let us say. I already have, and I am doing this reaction at some 400 degrees Celsius. I do not know where she does the reaction, I can check with her. Let us say the reaction is being done at 400 degrees Celsius. At 10 power minus 7 torr, we said how many oxygen atoms are there? There are about 10 power 14 or 10 power 13 oxygen, so in that order, right. So it is 21% is oxygen, let us say, in the entire air molecules that I have. So there are about 10 power 13 oxygen molecules, and 10 power 13 oxygen molecules are enough to oxidize bismuth selenite, right. And so this 10 power minus 7 base pressure, torr base pressure, is not good enough, especially if you are growing these sort of materials called the chalcogenides, right. So these materials like bismuth selenide, indium selenide, right, bismuth telluride. So all these are, they have their own nice properties and advantages. These are all quantum materials in some sense. Everything belongs to the group of what is called chalcogenides, but chalcogenides have a property of easy oxidation. We will actually see, we will look at some case studies when we go much deeper into thermodynamics and see, so how is oxidation a competing reaction, right. So oxidation, so so when I wanted to grow bismuth selenide, but I did not make sure that I have removed all the oxygen from the system, right. I still have about 10 power 13 oxygen molecules, and so I end up getting some partly bismuth selenide, partly bismuth oxide, and so a combination of everything, or some oxidized, some bismuth oxy Bi2Se3OX, right. So bismuth some oxy selenide or something like that, right. So and so this is going to affect my properties. This will interrupt the properties that I am going to look for. Right. So as a result, you need to pump down more, right. So in this MBE chamber that Dhavla had constructed all by herself in our lab, in our department, so she can ideally, so she uses what are called, so there is a roughing pump, that is step 1. There is a turbomolecular pump, that is step 2. And beyond that, use what are called ion pumps, right. So you ionize these gas molecules, and then so then the positive charge gets attracted to the anode, the negative charge to the cathode, and so on. So this is step 3, and going from step 2 to step 3, this is 10 power minus 7 torr. I am going down to about 10 power minus 10 torr, and going up to about 10 power minus 10 torr is what is called ultra high vacuum, right. So this is ultra high vacuum, and if I then count the number of gas molecules there, in about 10 power minus 10 torr I have 10 power 10 oxygen molecules, and turns out at 10 power 10 oxygen molecules, the pressure is so small, the partial pressure of oxygen is so small that I am not reacting, or the amount of oxygen that reacts with my bismuth selenide is negligible, that I get pure or nice bismuth selenide single crystalline thin films. right. So, if you ask me the question what is the base pressure I should go to grow my compound, to grow my material, I am going to ask you, right, so what is your material, right. If you are dealing with oxides or something like that, it may be okay, you just need a turbomolecular pump, you do not need to create all this fuss of going to ultra high vacuums. But if you want to grow these topological materials such as chalcogenides, which have the propensity to oxidize, right. So, oxygen can easily come and replace selenium sites, right, and that is a problem, correct. So, I do not want to make oxides, rather I want to make selenides, I want to make sulfides and so on, right. So, as a result, so I want to ideally use ultra high vacuum, in my, and then use a technique such as molecular beam epitaxy, so that I am able to do this 2 to 3 ratio very nicely. I am able to precisely control the flow of my precursors, right. So, the bismuth, the bismuth, the selenium and so on and so forth. Okay. Okay. Now, the question is, using all these pumps, right, so I can remove air molecules at a rate that I like, right. So, I have control over how much I remove. Using vacuum pumps, I can create vacuum, right, just like using heater coils, I can heat the material, right. But it is not just enough to create vacuum, it is not just enough to remove the pressure or remove the air molecules, you should be able to measure the pressure. And how do we measure pressure? We measure pressure using what are called pressure gauges, and these are also, I use different pressure gauges at different levels of vacuum. But so I have pressure gauges, I also urge you to go and study about various types of pressure gauges. Okay. So, measure the pressure using pressure gauges, similar to so we can also measure temperature using thermocouples. Okay. And then I need a control system, again my PID system, to actually set the correct pressure, right. So, in the chamber, right. Similarly, here also I have a control system to set the correct temperature, right. Now, if I have all these three, one is I know how to change the pressure or change the temperature, then the second one is I know, so in the checklist that I have, I know how to change the pressure, sorry, let me just do this, and here I know how to change the temperature, I know how to measure the temperature that I have changed, measure the pressure that I have changed, and I have a control system to go to a set temperature or set pressure. Then I say that so whatever I am controlling, right, I have complete control over these thermodynamic parameters. And in that sense, experimentally, temperature and pressure are best controllable. Okay. Now, if temperature and pressure are best controllable in a vacuum chamber, and I am going to do all my growth in some kind of a vacuum chamber, right, so a lot of physical vapor deposition processes and chemical vapor deposition processes happen in these vacuum chambers. I need to create some vacuum. Okay. So then the relevant potential for me to look at to study equilibrium in these systems is G, right, because G is dependent on temperature and pressure. I can change G, you have seen this, dG equal to minus V dP plus S dt. I can change V by changing pressure and temperature, correct. So, since G is dependent on both pressure and temperature, right. So, I can independently control temperature and pressure, and I can control them because I have the technology to control it. Okay. So, the relevant free energy relevant thermodynamic potential for experimental growth of materials is G. Okay. That is Gibbs free energy. All right. Okay. So, then so let us then for this class halt here, right, and in the next class we are going to look at continue on these ideas of G, looking at the potentials, and if there are other potentials we will look at these other potentials. and so we will build up on the language that we have developed so far, right. So and then so trying to correlate it with how it is useful in the growth process. Okay, so we'll continue the same exercise in the next class. Okay, see you all in the next class.